We believe enabling people with no software development skills like nurses and teachers to program robots in human environments such as nursing homes and schools could increase access to expensive services like elder care and education. Recently, block-based visual programming has become a popular approach to enable non-experts to program robots. However, when it comes to programming human-robot interactions, block-based visual programming has limitations, especially in terms of expressing concurrent behaviors. Concurrency is the ability of a program to do two or more things at the same time. It is critical in HRI because robots have multiple channels to communicate, and the channels need to be used simultaneously to create natural and robust interactions. Existing block-based programming interfaces support concurrency in ad hoc and inconsistent ways. For example, to make a robot play a sound and shimmying at the same time, robot action blocks like play sound should be non-blocking, meaning it should start playing the sound and move on to the next block immediately after. At the same time, making a robot to navigate to a location while allowing for a human to interrupt its navigation requires special blocks like go to until touched that combine an action with a perception event. Based on our experiences and reviewing the literature, we argue that a programming interface for authoring human-robot interactions must support expressing concurrency with ease. Our research question is, how should we design a concurrency interface for block-based visual programming in the context of programming interactive robots? Typical block-based programming systems consist of, first, a set of robot actions that are designed to achieve use cases, and second, an open-source visual programming library like Blockly that allows wrapping an existing programming language like Python. An expressive API is at the core of enabling intuitive concurrency interfaces. Hence, we first present our robot API. Let's say we want to create a block-based visual programming system for a simple tabletop robot that can speak, listen, and display and sense things on the screen. Here is a set of available actions defined as functions. We provide two versions of each action, with blocking functions that blocks the program until the action is done, and non-blocking functions that only start the action and immediately moves on to the next statement in the program. We also introduced two types of events, externally triggered and action-triggered events. We then provide three types of functions for users to work with events when programming a robot. Building on this low-level API, we propose three high-level block-based visual concurrency interfaces: Async, Callback, and WaitFor. The Async interface enables concurrency using asynchronous procedure calls, which represent a traditional approach for enabling concurrency in an imperative programming language. The Callback interface represents event-driven programming paradigm, which is common in UI programming languages. Finally, the WaitFor interface is inspired by event synchronization utilities involving promises. They encourage writing concurrent code while staying in an imperative mood. Let's say we want to make the robot say a long greeting sentence and monitor if the human says something in parallel, and move on to the next action of displaying on standby when it finishes speaking or when the human interrupts the robot. For the async interface, all actions are non-blocking. So we'll have to use a loop to make the robot wait for one of the two event occurrences. The callback interface provides the when construct that allows us to register a callback function finish with event handling logic in it. The WaitFor interface provides blocking functions for actions and waiting for events, and WaitFor one construct that holds the program execution until one of the two blocking functions finishes. So we can just use that. We first compared the three interfaces systematically by creating representative unit programs and measuring metrics like average number of blocks. Next, we conducted a user study to compare the ease of use of three proposed concurrency interfaces. We recruited participants with some programming but no robotics experiences. The study was conducted online, and participants used a web UI to program and test the instructed task with a simulated robot face. The main task of the user study was to create realistic human-robot interaction programs that involves three concurrency patterns, which are waiting for two parallel actions to finish, waiting for an action to finish and an event to happen, and waiting for one of the two events to happen. We examined participants' program to measure the ease of use. Specifically, we counted the number of blocks used in each program to measure the conciseness and the correctness by scoring each program using a rubric. We observed that the WaitFor concurrency interface produced the most concise and correct programs. And the callback interface was the most difficult to use. Investigating the programs created using the callback interface, we noticed that many participants made multiple mistakes while attempting to manually create event loops. We present the full analysis, results, and discussions in our paper. Thank you.